We begin tonight with a gentle exploration of one of the most carefully tested frameworks in modern physics. There is no need to stay awake for what follows. You may drift in and out of sleep at any point, and each part of our discussion will make sense on its own. We are here simply to move through ideas at a calm, unhurried pace. Tonight we turn our attention to the theory of relativity, a description of how space, time, and motion relate to one another. This is not a dramatic story with surprising twists. It is instead a slow examination of measurements, observations, and the careful work that physicists have done over more than a century to understand how the universe operates when we look closely at the nature of motion and gravity. We'll move through these ideas without excitement or urgency. The concepts we discuss have been tested extensively through experiment and observation. They form part of the accepted foundation of modern physics, used daily in technology and research. We approach them as we would approach any other aspect of the natural world, with patience, clarity, and respect for what can be measured and verified. Before we can discuss relativity itself, we need to establish what physicists mean by certain fundamental terms. These are words we use in everyday life, but in physics they carry specific meanings that we must understand clearly. When we speak of space, we mean the three-dimensional expanse in which objects exist and events occur. Space is where things are located. In classical thinking, space was considered an absolute backdrop, a fixed stage on which the universe played out. We could imagine space as extending infinitely in all directions, unchanging and the same for all observers regardless of their motion or position. Time, in everyday experience, is the progression of moments from past to future. We measure time with clocks. In classical physics, time was also treated as absolute, a universal ticker that advanced at the same rate for everyone, everywhere. The second that passed for someone standing still was thought to be exactly the same second that passed for someone moving rapidly. Motion refers to the change of position over time. When we say an object is moving, we mean its location in space changes as time progresses. Motion seems straightforward in daily life. A car moves down a road. A bird flies through the air. But in physics we must be more careful. Motion is always relative to something else. The car moves relative to the road. The bird moves relative to the ground. There is no absolute motion in space, only motion with respect to other objects or reference frames. A reference frame is simply a perspective from which we make measurements. If you are sitting in a train, you have one reference frame. Someone standing on the platform has another. The measurements you each make of the same event may differ, and understanding how those measurements relate to one another is central to physics. In our everyday experience, we rely on intuition built from the speeds and distances we encounter regularly. Objects move at walking pace or driving pace, or perhaps the speed of a fast aircraft. At these speeds, the differences between reference frames are small and hardly noticeable. Time seems to flow the same for everyone. Lengths appear the same regardless of motion, but intuition built at everyday speeds does not necessarily hold when we examine motion at very high speeds or in very strong gravitational fields. Physical measurement differs from intuition. Intuition is a mental shortcut useful for navigating daily life. Physical measurement is a careful process using instruments, clocks, rulers, detectors that can be calibrated and compared. When we rely on measurement rather than intuition, we sometimes find that nature behaves differently than we expect. Classical physics, developed over centuries and formalized by Newton and others, worked extremely well for describing motion at everyday speeds and scales. It predicted the paths of projectiles, the orbits of planets, the behavior of machines. But by the late 19th century, physicists encountered puzzles that classical physics could not resolve. One puzzle involved light. Light, we learned through experiment, is an electromagnetic wave. Waves in classical thinking require a medium to travel through. Water waves move through water. Sound waves move through air. What did light waves move through? Physicists proposed a substance called the luminiferous ether, an invisible medium filling all of space, through which light propagated. If the ether existed, then the Earth's motion through it should affect the measured speed of light. Light travelling in the direction of Earth's motion through the ether should have a different measured speed than light travelling perpendicular to that motion. Classical physics predicted this difference clearly, but the measurements disagreed. No matter how carefully experiments were designed, the speed of light appeared to be the same in all directions, regardless of the Earth's motion. This was deeply puzzling. It suggested that something fundamental about our understanding of space, time, and motion needed to change. The measurements also revealed something else important. The speed of light in vacuum was always measured to be the same value, approximately 300 million meters per second, regardless of the motion of the source or the observer. This constancy seemed to contradict the way velocities add in classical physics. If you throw a ball forward from a moving train, the ball's speed relative to the ground is the train's speed plus the throwing speed. But light did not behave this way. Its measured speed did not depend on the motion of the source. These observations led physicists to recognize that measurements of space and time depend on the observer's state of motion. The measurements of Bamans are not illusions or errors. They are real physical effects that must be accounted for. The framework that accomplishes this accounting is relativity. To understand how relativity emerged, we must look briefly at the foundations that came before it. Classical physics rested on the work of many thinkers, but Isaac Newton's formulation in the 17th century provided a comprehensive framework. Newton described motion using 3 laws and introduced the concept of universal gravitation. In Newton's framework, space and time were absolute. Space was a fixed container. Time flowed uniformly everywhere. If 2 events occurred simultaneously in one location, they occurred simultaneously everywhere. Motion was relative. You could measure velocity relative to different reference frames, But the transformations between reference frames were simple. Velocities added together in a straightforward way. This framework worked beautifully for centuries. It predicted planetary motion with great accuracy. It explained tides, projectile paths, mechanical systems. But as experimental techniques improved in the 19th century, physicists began to probe phenomena that classical physics could not fully explain. James Clerk Maxwell, in the mid-19th century, developed a complete theory of electromagnetism. His equations described how electric and magnetic fields behave and propagate. One consequence of Maxwell's equations was that electromagnetic waves travel at a specific speed in vacuum, the speed of light. This speed emerged naturally from the equations determined by fundamental constants related to electricity and magnetism. But Maxwell's equations did not include any reference to the motion of the observer or the source. The speed of light seemed to be a constant value built into the structure of electromagnetism itself. This raised a question: constant relative to what? Physicists assumed the answer was the ether, the hypothetical medium through which light waves propagated. The speed of light would be constant relative to the ether. Observers moving through the ether would measure different speeds for light depending on their motion. This seemed consistent with how other waves behaved. Albert Michelson and Edward Morley in 1887 designed an experiment to detect the Earth's motion through the ether. They used an interferometer, a device that splits a beam of light, sends the parts along perpendicular paths, and then recombines them. If the Earth were moving through the ether, light travelling parallel to the motion should take a different time to complete its path than light travelling perpendicular. This time difference would show up as a shift in the interference pattern when the beams recombined. The experiment was sensitive and carefully executed. Michelson and Morley expected to measure a clear signal of the Earth's motion through the ether. Instead, they found no signal at all. No matter how they oriented the apparatus or when they performed the experiment, the speed of light appeared to be the same in all directions. This result was repeated and refined by others. The conclusion became unavoidable. There was no detectable ether wind. The speed of light did not vary with the observer's motion in the way classical physics predicted. Several explanations were proposed. Some suggested the ether was dragged along with the Earth. Others proposed that objects contracted when moving through the ether in just the right way to hide the effect. These explanations became increasingly complicated and ad hoc. None of them addressed the deeper issue. Why should nature conspire to make the speed of light appear constant? Albert Einstein, in 1905, approached the problem differently. Rather than trying to preserve absolute space and time by adding new assumptions, he asked what would follow if the constancy of the speed of light were taken as a fundamental principle. He also insisted on another principle. The laws of physics should be the same in all inertial reference frames. That is, all reference frames moving at constant velocity relative to one another. These two principles, the constancy of the speed of light and the equivalence of inertial frames, formed the foundation of special relativity. Einstein showed that if you accept these principles, then space and time cannot be absolute. They must be relative. The measurements of time intervals and spatial distances must depend on the observer's state of motion. This was not a small adjustment to classical physics. It was a fundamental reconception. Space and time were not separate, absolute entities. They were interwoven into a single structure, space-time, and measurements of distance and duration depended on the reference frame. Importantly, this was not speculation. Einstein's framework made specific predictions that could be tested experimentally. Over the following decades, those tests were performed, and the predictions were confirmed again and again. Later, Einstein extended these ideas to include gravity. Special relativity applied to inertial frames, reference frames moving at constant velocity. But gravity involves acceleration, objects fall, orbits curve. Einstein recognized that gravity could not be described simply as a force acting in flat spacetime. In 1915, he published The General Theory of Relativity, which described gravity as a consequence of the curvature of spacetime itself. General relativity also made testable predictions. Light should bend when passing near massive objects. Orbits should behave slightly differently than Newton's theory predicted. Time should pass at different rates in different gravitational fields. These predictions, too, were tested and confirmed. Relativity emerged not from speculation or philosophy, but from careful attention to what could be measured. It replaced assumptions that seemed obvious, absolute space, absolute time, with a framework that matched the actual behavior of nature. Special relativity rests on two postulates. These are starting assumptions, accepted because they match observation and because the framework built from them successfully describes nature. The first postulate is that the laws of physics are the same in all inertial reference frames. An inertial reference frame is one that is not accelerating. It moves at constant velocity or is at rest. If you perform an experiment in a laboratory on Earth and someone else performs the same experiment in a laboratory on a spacecraft moving at constant velocity, far from any gravitational influences, you both find the same laws governing the experiment. Electricity behaves the same way, magnetism behaves the same way, light behaves the same way. There is no preferred reference frame, no absolute state of rest. The second postulate is that the speed of light in vacuum is constant for all inertial observers, regardless of the motion of the light source or the observer. If you shine a flashlight while standing still, the light travels at a particular speed. If you shine a flashlight while running, the light still travels at that same speed relative to you. If someone standing still measures the speed of your light beam, they also measure it to be that same speed, even though you are moving. The speed of light in vacuum is always measured to be approximately 300 million meters per second, denoted by the letter C. These two postulates lead directly to the conclusion that simultaneity is relative. Two events that occur at the same time, according to one observer, may occur at different times according to another observer in motion relative to the first. This is not a matter of perception or delay in signals. It is a fundamental feature of how time is measured. Consider two observers. One stands on a train platform. Another sits in a train moving at constant velocity past the platform. A light source at the center of the train car emits a flash of light. The light spreads out in all directions at speed c. For the observer on the train, the light reaches the front and back walls of the car simultaneously, because the observer is at rest relative to the car and the distance to each wall is the same. But for the observer on the platform, the situation is different. The train is moving. By the time the light reaches the back wall of the car, that wall has moved forward slightly toward where the light was emitted. By the time the light reaches the front wall, that wall has moved forward slightly away from where the light was emitted. Because the speed of light is the same for both observers, the observer on the platform measures the light reaching the back wall before it reaches the front wall. The events are not simultaneous in the platform frame. This is not an illusion. Both observers are making correct measurements in their respective frames. The order of events, whether two things happen at the same time, depends on the motion of the observer. Simultaneity is relative. From this relativity of simultaneity follows another consequence: time dilation. A clock moving relative to an observer runs slow compared to a clock at rest in the observer's frame. This is a measured effect. It is not that the moving clock malfunctions. The passage of time itself, as measured, depends on motion. Imagine a simple clock made of light. A pulse of light bounces up and down between two mirrors. Each round trip is one tick. For an observer at rest relative to this clock, the light travels straight up and down. The time for one tick is the distance between the mirrors divided by the speed of light. Now consider this clock moving sideways relative to another observer. For that observer, the light must travel a longer path for each tick, because while the light is in flight, the clock has moved sideways. The light traces out a diagonal path rather than a straight vertical path. Since the speed of light is the same for both observers and the path is longer, the time for one tick is longer. The moving clock ticks slower. This is not specific to light clocks. All physical processes run slower when measured by an observer relative to whom those processes are moving. Time dilation is a property of time itself, not of particular mechanisms. Length contraction is another consequence. An object moving relative to an observer is measured to be shorter along the direction of motion than it is when at rest in the observer's frame. Again, this is a real measurement, not an optical illusion. The object's length in its own rest frame is its proper length. When measured by someone relative to whom the object is moving, the length is contracted. The mathematics of special relativity relates measurements valued in different reference frames through what are called Lorentz transformations. These transformations account for the constancy of the speed of light and ensure that all observers, regardless of their motion, agree on the laws of physics, even though they measure different values for time intervals and distances. Importantly, these effects become noticeable only at speeds that are a significant fraction of the speed of light. At everyday speeds, walking, driving, even the speed of a fast aircraft, the effects are extremely small, far too small to notice without precise instruments. This is why classical physics works so well for everyday experience. But at high speeds, the effects are large and must be taken into account. Special relativity also unifies space and time into space-time. An event is something that happens at a particular place and a particular time. In space-time, an event is a point. The separation between two events has both a spatial component and a time component. Different observers moving relative to one another divide this separation differently between space and time, but the underlying space-time structure is the same for everyone. The framework also shows that mass and energy are related through the famous equation E equals mc squared, where E is energy, m is mass, and c is the speed of light. This equation tells us that mass is a form of energy. A small amount of mass corresponds to a very large amount of energy because the speed of light is very large. This relationship has been confirmed in countless experiments and is the basis for understanding nuclear reactions and the behavior of elementary particles. It is essential to emphasize that special relativity is not about appearances or tricks of perception. It describes how measurements actually differ between observers in different reference frames. When we say a moving clock runs slow, we mean that careful measurements using synchronized clocks in the observer's frame will show fewer ticks on the moving clock. When we say a moving object is contracted, we mean that careful measurements of its length in the observer's frame will yield a shorter value than its rest length. These are not contradictions or paradoxes. They are consistent features of a universe in which the speed of light is constant and the laws of physics are the same in all inertial frames. Once we accept what measurements show, the framework of special relativity follows necessarily. To make these concepts more concrete, we can consider specific examples where relativistic effects have been observed and measured. One of the earliest confirmations of time dilation came from studying particles called muons. Muons are created high in Earth's atmosphere when cosmic rays, high-energy particles from space, collide with atmospheric molecules. Muons are unstable. They decay into other particles. The average lifetime of a muon at rest is about 2 microseconds. Given this lifetime, classical physics predicts that muons created in the upper atmosphere should decay long before reaching the ground. Even travelling at speeds close to the speed of light, they should not survive the journey. Yet muons are detected at Earth's surface in large numbers. Time dilation explains this. From the perspective of an observer on the ground, the muon is moving at high speed. Its clock, its internal decay process, runs slow. The 2 microsecond lifetime is extended by the time dilation factor, allowing the muon to travel much farther for decaying. Measurements of muon arrival rates and energies match the predictions of special relativity precisely. From the muon's perspective, in its own reference frame, it lives for only 2 microseconds, but the distance it must travel to reach the ground is contracted due to length contraction. The atmosphere is thinner in the muon's frame, so the muon has enough time, by its own clock, to reach the ground. Both perspectives, time dilation in the ground frame, length contraction in the muon frame, are consistent. Another everyday example of relativity in action is the Global Positioning System, or GPS. GPS relies on a network of satellites orbiting Earth. Each satellite carries a precise atomic clock. The satellites broadcast timing signals. A GPS receiver on Earth uses signals from multiple satellites to determine its position by calculating the travel time of the signals. For GPS to work accurately, the clocks on the satellites must be synchronized with clocks on the ground to within a few nanoseconds. But the satellites are moving relative to the ground, and they are also at a higher altitude in Earth's gravitational field. Both special relativity and general relativity affect the rate at which the satellite clocks tick. Due to their motion, special relativity predicts that the satellite clocks should run slow relative to ground clocks. Due to being higher in the gravitational field, general relativity predicts that the satellite clocks should run fast relative to ground clocks. Both effects are real and they partially offset each other, but the general relativistic effect is larger. The net result is that satellite clocks, if not corrected, would run fast by about 38 microseconds per day compared to ground clocks. This may seem like a tiny amount, but light travels about 30 centimeters in 1 nanosecond. A timing error of 38 microseconds would cause position errors of more than 10 kilometers per day. GPS would be useless. Engineers account for relativistic effects by adjusting the rate of the satellite clocks before launch. The system works because relativity is taken into account. These are not isolated examples. Particle accelerators around the world routinely accelerate particles to speeds very close to the speed of light. The behavior of these particles, their lifetimes, their energies, the way they collide and produce new particles, is described accurately by special relativity. Engineers designing accelerators must use relativistic equations. Classical physics would give completely wrong predictions. In every case where relativistic effects are large enough to measure, the measurements confirm the predictions of special relativity. The framework is not speculative. It is a well-tested description of how nature operates. Thought experiments also help us understand the framework, even if we cannot perform them in practice. Einstein often used thought experiments to clarify concepts. The light clock example we discussed earlier is one such thought experiment. It illustrates time dilation without requiring complex mathematics. Another thought experiment involves two twins. One stays on Earth. The other travels on a very fast spacecraft to a distant star and returns. Due to time dilation, less time passes on the moving twins' clock than on the Earth twins' clock. When they reunite, the travelling twin is younger. This is sometimes called the twin paradox, but it is not a paradox. It is a consistent consequence of relativity. The situation is not symmetric, because the travelling twin must accelerate, change velocity, to turn around and return. Acceleration breaks the symmetry, and general relativity, which includes accelerating frames, explains the situation completely. These examples and thought experiments help build intuition, but the foundation remains measurement. Relativity describes what we measure, not what we imagine or assume. The measurements show that space and time are not absolute. They depend on motion. The framework of special relativity accounts for this dependence in a consistent, mathematically precise way. Special relativity applies to inertial reference frames, frames moving at constant velocity. But the universe contains gravity, and gravity involves acceleration. Objects fall, planets orbit. To include gravity, Einstein extended relativity to non-inertial frames. The key insight came from considering the equivalence of gravitational and inertial mass. Gravitational mass determines how strongly an object responds to gravity. Inertial mass determines how much an object resists acceleration. Experiments showed that these two masses are the same, to very high precision. This is not obvious. They could, in principle, be different, but nature makes them equal. Einstein recognized that this equivalence means that gravity can be understood as a feature of space-time geometry rather than as a force. Imagine being in a closed box with no windows. If the box is sitting on Earth's surface, you feel gravity pulling you down. If the box is in space, far from any gravitational source, and is being accelerated upward at a rate equal to Earth's surface gravity, you would feel the same downward pull. Locally, inside the box, you cannot distinguish between the two situations. This equivalence principle suggests that what we call gravity is not a force in the usual sense. It is instead a consequence of how space-time itself is shaped. In special relativity, space-time is flat. Events are points in a four-dimensional space-time, and the separation between events is described by a geometry that does not curve. But in general relativity, space-time can curve. Mass and an energy cause this curvature. Objects moving through curved space-time follow paths that appear in our three-dimensional perspective to be curved paths under the influence of gravity. This is not easy to visualize because we cannot directly see four-dimensional space-time. Analogies help. Imagine a stretched rubber sheet. Place a heavy ball in the center. The sheet curves around the ball. Now roll a smaller ball across the sheet. Its path curves because the sheet is curved. The smaller ball is not pulled by a force. It simply follows the straightest path it can on the curved surface. In a similar way, planets orbit the Sun, not because the Sun exerts a force pulling them, but because the Sun's mass curves the space-time around it, and the planets follow the natural paths called geodesics through that curved space-time. A geodesic is the closest thing to a straight line in a curved space. General relativity is mathematically complex. It relates the curvature of space-time to the distribution of mass and energy through a set of equations called the Einstein field equations. We will not attempt to write these equations or solve them here. What matters for our purposes is the conceptual picture. Mass and energy tell space-time how to curve, and space-time tells objects how to move. The curvature affects not only the paths of objects, but also the passage of time. Clocks closer to a massive object run slower than clocks farther away. This is gravitational time dilation. It is distinct from the time dilation due to motion in special relativity, but it arises from the same underlying framework, general relativity, which unifies both effects. Light is also affected by space-time curvature. Light follows geodesics, just as massive objects do. If space-time is curved, the path of light curves as well. This means that light passing near a massive object bends. The effect is small, but it can be measured. General relativity predicts phenomena that have no counterpart in classical physics. Black holes are regions where space-time curvature becomes so extreme that not even light can escape. Gravitational waves are ripples in space-time itself, caused by accelerating masses that propagate outward at the speed of light. Both of these predictions have been confirmed by observation. It is important to recognize that general relativity does not eliminate Newton's theory of gravity. Newton's theory remains an excellent approximation in most situations. For planetary motion in our solar system, the differences between Newton's predictions and general relativity's predictions are tiny. Only in very strong gravitational fields or over very precise measurements do the differences become significant. General relativity extends and refines our understanding of gravity, but it does so in a way that is consistent with classical physics in the appropriate limits. This is a feature of good scientific theories. They do not discard what came before, unless what came before is clearly wrong. They encompass it and extend it. General relativity has been tested in many ways. These tests use natural phenomena and carefully designed experiments to check whether the predictions of the theory match what we observe. Planetary orbits provide one test. Newton's theory predicts that planets follow elliptical orbits around the Sun. The orbit of each planet is fixed in space. General relativity predicts almost the same orbits, but with a small difference. The point of closest approach to the Sun, called the perihelion, shifts slightly with each orbit. The orbit itself precesses slowly over time. For most planets, this precession is tiny and dominated by other effects, such as the gravitational pull of other planets. But for Mercury, the innermost planet, the precession predicted by general relativity is measurable. Observations showed that Mercury's perihelion precesses by about 43 arcseconds per century more than Newton's theory predicts. General relativity accounts for this excess precession exactly. This was one of the early confirmations of general relativity. It showed that the theory could explain an observed anomaly that classical physics could not. Another test involves light. If space-time is curved by mass, then light passing near a massive object should follow a curved path. The sun is massive enough to produce measurable bending of light. During a total solar eclipse, when the sun's brightness does not overwhelm the light from distant stars, astronomers can photograph stars that appear to be near the sun in the sky. If the sun were not there, the stars would appear in certain positions. With the sun present, its gravity bends the light from those stars, and they appear to be slightly displaced. This test was first carried out in 1919 during a total solar eclipse. Measurements confirmed the bending of starlight by an amount consistent with general relativity's prediction. The effect is small, about 1.5 arcseconds for light just grazing the sun's surface, but it was measurable with the instruments of the time. Today, light bending is observed routinely in astronomical contexts. Distant galaxies act as gravitational lenses, bending the light from even more distant objects behind them. This gravitational lensing creates distorted images, multiple images, or arcs of light in the sky. The amount and pattern of distortion allows astronomers to map the distribution of mass in the lensing galaxy, even mass that does not emit light. Gravitational lensing is one of the tools used to study dark matter and the large-scale structure of the universe. Gravitational time dilation has also been tested precisely. Atomic clocks are accurate enough to measure tiny differences in the passage of time. Experiments have placed atomic clocks at different altitudes and compared their rates. Clocks at higher altitude, farther from Earth's center, and thus in a weaker gravitational field, run faster than clocks at lower altitude. The measured differences match the predictions of general relativity to high precision. One experiment placed atomic clocks on commercial aircraft and flew them around the world. When compared with clocks that remained on the ground, the airborne clocks showed a difference consistent with both the gravitational time dilation due to higher altitude and the time dilation due to motion. Both effects are real and were measured. Black holes are another consequence of general relativity. If enough mass is concentrated in a small enough region, the space-time curvature becomes so strong that nothing inside a certain boundary, called the event horizon, can escape. Not even light. The interior of the event horizon is cut off from the outside universe. Black holes are not speculative. they have been observed indirectly and directly. Astronomers observe stars orbiting around massive, invisible objects at the centres of galaxies, including our own Milky Way. The orbits indicate the presence of objects millions of times the mass of the Sun, confined to very small volumes. The only objects that fit these observations are black holes. In recent years, astronomers have imaged the region around a black hole directly. Using a network of radio telescopes around the world, they captured images of the glowing gas orbiting the supermassive black hole at the centre of the galaxy M87. The images show a dark region, the shadow of the event horizon, surrounded by a bright ring of emission. The size and shape of the shadow match general relativity's predictions. Gravitational waves are ripples in space-time itself, predicted by general relativity. When massive objects accelerate, particularly in very strong gravitational fields, they can emit gravitational waves that carry energy away from the system. These waves travel at the speed of light and stretch and squeeze space-time as they pass. Detecting gravitational waves is extremely difficult because the effects are tiny. But in 2015, the Laser Interferometer Gravitational Wave Observatory, or LIGO, succeeded. LIGO detected gravitational waves from the merger of two black holes more than 1 billion light years away. Since then, many more detections have been made, including waves from merging neutron stars. These detections confirm that gravitational waves exist, that they propagate at the speed of light, and that their properties match the predictions of general relativity. Gravitational wave astronomy is now an established field, opening a new way to observe the universe. All of these phenomena, perihelion precession, light bending, gravitational time dilation, black holes, gravitational waves, are consequences of general relativity. They were predicted by the theory before they were observed, or they are explained by the theory in cases where classical physics cannot explain them. The consistency between prediction and observation gives us confidence that general relativity is an accurate description of gravity. Relativity connects to many other areas of physics and has implications across scientific disciplines. Cosmology, the study of the universe as a whole, relies fundamentally on general relativity. The framework allows physicists to describe the large-scale structure and evolution of the universe. According to general relativity, the universe can be expanding or contracting. The equations relate the rate of expansion to the total mass and energy content of the universe. Observations show that the universe is expanding. Distant galaxies are moving away from us, and the farther away they are, the faster they move. This expansion is consistent with general relativity. The theory also predicts that the expansion was much more rapid in the very early universe, a period called cosmic inflation. While details of inflation are still being worked out, the general framework is part of the standard model of cosmology. General relativity also predicts that the expansion rate can change over time depending on the energy content of the universe. Observations indicate that the expansion is currently accelerating. driven by something called dark energy. The nature of dark energy is not fully understood, but its existence is inferred from measurements of distant supernovae and other cosmological observations. General relativity provides the framework within which these observations are interpreted. The theory also describes how light travels across vast cosmological distances. Light from distant galaxies is shifted toward longer wavelengths, an effect called redshift, because the universe has expanded while the light was in transit. The amount of redshift tells us how much the universe has expanded since the light was emitted. This allows astronomers to measure distances to remote objects and to map the history of the universe. Relativity also intersects with quantum mechanics, the theory governing the behavior of atoms and subatomic particles. Quantum mechanics is extraordinarily successful in describing the microscopic world, but it was developed initially in a framework that treated time and space separately, as in classical physics. Combining quantum mechanics with special relativity led to quantum field theory, which describes particles and fields in a way that respects relativity. Quantum field theory is the foundation of the standard model of particle physics, which explains the electromagnetic, weak, and strong nuclear forces. These theories have been tested to extreme precision. Every particle collider, every experiment in particle physics confirms that the quantum world respects the principles of special relativity. However, combining quantum mechanics with general relativity, quantum gravity, remains an unsolved problem. General relativity describes gravity as Z-shaped space-time curvature, a smooth, continuous geometry. Quantum mechanics describes the world as fundamentally probabilistic and discrete. Finding a consistent quantum theory of gravity is one of the major challenges in theoretical physics. Several approaches are being explored, such as string theory and loop quantum gravity, but none has been confirmed experimentally. This is not a failure of general relativity or quantum mechanics. It is a recognition that each theory has a domain where it applies. General relativity works beautifully for describing gravity on large scales, from planets to galaxies to the entire universe. Quantum mechanics works beautifully for describing matter and forces at microscopic scales. The question is how to describe situations where both gravity and quantum effects are strong, such as inside black holes or during the very first moments after the Big Bang. In practical terms, relativity also influences technology beyond GPS. Particle accelerators, as mentioned, rely on relativistic mechanics to predict how particles behave at high speeds. Synchrotron light sources, which produce intense X-rays for research, operate using principles from special relativity. Even some medical imaging techniques rely on the production of particles whose behavior is governed by relativistic physics. Relativity has also shaped the way physicists think about the universe. It showed that space and time are not fixed background structures, but are dynamic and participant in physical processes. It demonstrated that intuition built from everyday experience can be misleading when extended to extreme conditions. It reinforced the importance of measurement and experiment over assumption and common sense. The theory also illustrates a key feature of scientific progress. Relativity did not emerge from pure speculation. It emerged from careful attention to experimental results that could not be explained by existing theory. It made specific, testable predictions, and those predictions were confirmed. It has been refined and tested over more than a century, and it continues to be consistent with all observations to date. As we move toward the close of our discussion, we can restate gently some of the central ideas we have explored. Space and time, which we experience as separate in everyday life, are unified into a single structure called space-time. Measurements of spatial distances and time intervals depend on the motion of the observer. This dependence is not a trick of perception. It is a fundamental feature of how nature operates. The speed of light in vacuum is constant for all observers, regardless of their motion or the motion of the light source. This constancy is a cornerstone of relativity. It leads directly to the conclusion that simultaneity is relative, that time dilates, and that lengths contract, all as measured effects depending on reference frames. Motion is always relative. There is no absolute rest, no privileged reference frame. The laws of physics are the same in all inertial frames. This symmetry is central to special relativity. Gravity, in the framework of general relativity, is not a force in the traditional sense. It is the curvature of space-time caused by mass and energy. Objects move along the straightest paths they can in this curved space-time. Those paths appear curved to us because the space-time itself is curved. The passage of time is affected by both motion and gravity. Clocks in motion relative to an observer run slow. Clocks in stronger gravitational fields run slow compared to clocks in weaker fields. These are real, measurable effects confirmed by countless experiments and integral to technologies we use daily. Relativity has been tested extensively. From the decay of particles high in the atmosphere, to the orbits of planets, to the bending of light by massive objects, to the precise timing required for satellite navigation, the predictions of relativity are confirmed again and again. Gravitational waves detected directly in recent years provide yet another confirmation. The framework connects to cosmology, explaining the expansion of the universe and providing the tools to study its history and structure. It connects to particle physics through quantum field theory, which combines quantum mechanics with special relativity. It remains a subject of active research, particularly in efforts to unify it with quantum mechanics into a theory of quantum gravity. What we have discussed tonight is not speculation. It is accepted science, the result of over a century of careful theoretical work and experimental testing. The ideas may seem strange when first encountered because they differ from everyday intuition, but they are consistent with what we measure, and that is what matters in physics. We have moved through these ideas slowly, describing them in prose without relying on mathematics. The mathematical framework of relativity is elegant and precise, but the concepts can be understood, at least in outline, through careful explanation and attention to what measurements reveal. We have now travelled through the central concepts of relativity, special relativity, which describes motion and the unity of space and time, and general relativity, which describes gravity as space-time curvature. We have seen how these ideas emerged from careful observation, how they have been tested and confirmed, and how they connect to other areas of physics. There is no need to retain every detail. The ideas are large, and understanding them fully takes time and reflection. You may have drifted in and out as we spoke, and that is entirely natural. Each section we discussed was intended to stand on its own, so that wherever your attention rested, you encountered ideas that were complete in themselves. The universe, as described by relativity, is a place where space and time are woven together, where motion is relative, and where gravity arises from the shape of space-time itself. These are not simply abstract ideas. They are tested descriptions of how nature behaves, used every day in research and technology, and refined through ongoing observation. We close gently without urgency as we began. The concepts we explored are part of the foundation of modern physics. They will remain where they are, available for reflection, should you wish to return to them. Rest now if you wish. There is nothing more required of you tonight.